We want to discuss double integrals and volumes. What does the double integral mean, and how can we use that to compute the volume? The double integral represents for us each integrand some dimension. And so the double integral would represent a two-dimensional spectrum, then coupled times a function, where the function would give us the height. And so we have the base area from the double integral. That gives us, from the previous section, the area, and then the base area times the height would give us the volume. So how do we build that? So we have a surface, z equal to f of xy, some graph, some function, where the height is given by the function f evaluated at each x sub i, y sub i. The so-called base area is found by delta a sub I. Then when we calculate the function, the height times the base area, we get the volume. We use the typical Riemann sum from Calculus 1 to compute this summation, the limit of that summation, as the partitions delta get smaller and smaller. We shrink the magnitude of these. In Calculus 1, we talked about rectangular slices. Here we talk about small cubes. And so here we add up all these cubes and shrink them, and that gives us the volume. You see each of these rectangular slices, but they become a cube because we talk about them in the third dimension, the base times its respective height. And so we partition, we slice up the surface in terms of all these cubes. Cubes are the same magnitude by all means, and thus using the limit of the partition getting smaller and smaller of the summation, we have the double integral. If this represents a positive value, that is, if f is positive, then that same double integral gives us the volume. A very fascinating word in mathematics, if f is integrable, that is that the function is continuous over the respected region R, and here that the limit exists by all means from this definition here. So if this limit exists, then we say that that the function is integrable. Now, if that be the case, let f be continuous on a plane region R. We keep talking about R, but R is the key. So let's define R. R is defined if it's vertically simple. X is bounded by A and B. We're on this interval from A to B, and that Y is bounded below and above by G sub 1 and G sub 2. G1 and G2, likewise with F, are continuous. Then we can write, according to Fubini's, we can write the double integral with now knowing the endpoints of integration, we can compute it. Likewise, if it's horizontally simple, y is bounded by c and some number c and d horizontal lines, and then x is bounded to the left by h sub 1 of y and to the right by h sub 2 of y. H1, H2 are continuous. Likewise, f is continuous on the interval from c to d with respect to y. You can compute the double integral using the endpoints. The key to this section, I think, chapter will be to determine the correct region R. Let's look at some problems. So here, set up the integrals for both orders of integration. I'm only going to just set up the double integral for just one and just solve it. So you understand here, this is a rectangle with vertices. So we're at the origin. X goes out to 3, and then y goes up to 5. Why did I start drawing this? I do not like to color. Guess if you start something, you gotta finish it. Boy, you get the idea. So look at x. X is bounded from 0 to 3. What about y? Y is bounded from 0 to 5. This, my friends, becomes the region. So here, this double integral now is x times y. We can do dy dx. Where y is bounded from 0 to 5 and x is bounded from 0 to 3. So integrate with respect to y, that gives us 1/2 y squared. Evaluate the y from 0 to 5. So we get 25. So we just say 25 over 2 times the integral from 0 to 3 x dx. You would agree with me that just setting up the double integral is the hard part. Integrating is straightforward. So integrate with respect to x, that's 1/2 x squared. So it's 25 over 4 times x squared. X is evaluated from 0 to 3. It gives us 9 times 25, or 225 all over 4. Setting up the double integral is the key, and coupled with that is to be able to determine the correct r. Now r here is fixed because here these are fixed vertices. But if you're given a function, then it's a little bit different. So here the region I have some function y equal to x. It's doing that. Then y equal to 2x there. And then x equal to 1, x equal to 2. So the region is there. So here the region is now said to be where x goes from 1 to 2, and then y is bounded below by x and bounded above by 2x. So this double integral is the integral. We always use the numbers for the outer integral, and then the functions, if that's the case, for the inner integral. Y over x squared plus y squared, and this is dy dx. Well, it seems that if we let y equal to x squared plus y squared, and then the dy would pick up this y dy, or that is 1/2. This implies that du, this is with respect to y, is 1/2 y, 2 times y dy. I'm skipping, jumping the gun. So 1/2 du is the y dy. So this is 1/2 times the integral, not from 0, but from 1 to 2, and this is 1 over u du, and then that dx out there. So we integrate. This is 1/2 times the integral from 1 to 2 of the natural log of u, but u is x squared plus y squared, evaluated from the y is evaluated from x to 2x, and then this is dx on the outside. So we have 1/2 times the integral from 1 to 2. This is the natural log of x squared plus y squared, but y is 2x. So y is 2x. So this is 2x squared. That's 4x squared. Then it's minus the natural log of x squared plus, here y is x, so this is x squared. Dx. 1/2 times the integral from 1 to 2. This is the natural log. You can add those up, so we get 5x squared, the natural log of 5x squared, minus the natural log of 2x squared dx. And that gives us 1/2 times the integral from 1 to 2. This is the natural log of 5 divided by 2. Right? We use that property from natural logs and from logarithms as well. So the natural log of 5x squared minus the natural log of 2x squared is the natural log of 5x squared divided by 2x squared, which is just the natural log of 5 over 2, which is a number. So in front we have 1/2 times the natural log 5 over 2 times the integral from 1 to 2 dx. That just gives us 1/2 times the natural log of 5 over 2. And this is times x evaluated from 1 to 2, which is just 1. So our answer is 1/2 times the natural log of 5 over 2. Let's look at this one. We have to do some graphing on this. So we have this y equal to 4 minus x squared and y equal to 4 minus x. Let's see where they intersect. They intersect when 4 minus x squared is set to equal to 4 minus x. So that gives us 0 is equal to x squared minus x. Well, this is just x times x minus 1 equal to 0. So this implies that x equal to 0, x equal to 1. So graphically, just give a sketch of a graph. Won't be picture perfect, but so 4 minus x is a straight line going down. And so here they share 4 when x is 0, right? And then they share 1. So this guy is doing that. And so the intersection and the region that's bounded is here. X equals 0, x equal to 1 is what we need. So our region is x is bounded below by 0 and above by 1, and then y is bounded below by that line 4 minus x, and above by the curve. See, the curve is on top of the line, so this is 4 minus x squared. Okay, so if that's the case, then we can just write it here and pull that -2 out in the front. It's the integral from 0 to 1. This is the integral from 4 minus x to 4 minus x squared. This is y becomes dy dx. Y is y because y is bounded below and above here by 4 minus x and 4 minus x squared. And why the dx out here? Because that represents this outer integral, which the bounds for x goes from 0 to 1. So we integrate here with respect to y, so that becomes 1/2 y squared. So I'm going to cancel out this 2 with that 1/2, so I just have left a negative integral from 0 to 1. This is y squared evaluated from 4 minus x to 4 minus x squared dx. Bring it downstairs. So this is negative the integral from 0 to 1. Now evaluate at 4 minus x squared. So this is 4 minus x squared to be squared because it's y squared, right? Then minus, we evaluate y squared at 4 minus x. This is to be squared dx. We simplify that. So we're going to write this as the integral from 0 to 1. We write this first. So this is 4 minus, just to take care of that negative sign, minus 4 minus x squared to be squared dx. Simplify that. Integral from 0 to 1. This is 16 minus 8x plus x squared. This is minus 16 plus 8x squared minus x to the 4th. I took care of that negative when I FOILed as well. Simplify, the 16's cancel out. This is the integral from 0 to 1 of, let's see, we got 8x squared plus x squared is 9x squared. We're not integrating that yet, we're just still simplifying. So those guys went out. This guy went with him. Oh, we got that big number there, that minus x to the 4th. That's there. And then we need minus 8x. Now we integrate. So this gives us 3x to the 3rd minus 1/5 x to the 5th minus 4x squared. That's evaluated from 0 to 1. So we get 3 minus 1/5 minus 4. So it gives us negative 1/5 minus 1, which is negative 6 over 5. Now, if we were computing the area, we'd have trouble, but we're not computing the area. We're computing the double integral, which just comes out to be an iterated integral. See, in the instructions, it doesn't say anything about the area. If it's area, then it has to be positive. If we're computing the area and we get a negative, then we oops somewhere. Okay, I got 2 more problems to do, but let me just work this one, and then I gotta eat some chicken and some cabbage and some rice. Okay, I hope you understand. Yeah, I'm getting hungry. So now this is the region. Graph the region, determine R, and that's important. Okay. So we're going to graph this. So this is this y equal to the square root of x. So it does that. Then it says y equals 0. Right? Y equal to 0 is the x-axis, and then x equal to 4. So this is our region here. So let's look at that. X is bounded from 0 to 4. And then y is bounded from 0 to the square root. This is R. So we got it. So this is the integral from 0 to 4. Always the numbers go on the outer integral. The inner integral, you can have functions there, because they'll be wiped out by the evaluation of the numbers toward the end. So this is y over 1 plus x squared. This is dy, right? The dy goes with the endpoints of the limits from 0 to the square root of x, and then afterwards dx, because dx corresponds with the interval from 0 to 4. So we integrate with respect to y first. This is the integral from 0 to 4, and that gives us, it's the 1/2 y squared. Can I put the 1/2 right there? And then this is y squared. It's a small 2. That's over 1 plus x squared, and the y is evaluated from 0 to the square root of x dx. So we evaluate with respect to y, or the y squared. It's 1/2 the integral from 0 to 4. So we have y, but it's the square root of x to be squared. That's all over 1 plus x squared. Evaluate at 0, we get 0, so it's just dx. So we have 1/2 times the integral from 0 to 4. It's just x over 1 plus x squared dx. So you know it's going to be a natural log. Let u equal to 1 plus x squared. Du is 2x dx. We get a 1/2 factor, right? So this is 1/2 times that 1/2 is 1/4 times the natural log of the absolute value of 1 plus x squared, and the x is evaluated from 0 to 4. So that gives us 1/4 times the natural log of 1 plus x to be squared is 16, minus 1/4 times the natural log of 1 plus 0. Well, the natural log of 1 is 0, so all we have left is just 1/4 times the natural log of 17. Let's just stop right there. It's time to eat. Thank you.